Welcome! My name is Owen Redwood, and this lecture is part of the Offensive Computer Security Open Courseware in 2015, hosted at hackallthethings.com. This lecture, Exploit Development 102, will cover a number of important topics and lead into the same slides for 103. The outline of today's talk is this time we're going to go over the foundations of writing shellcode, taking you through multiple steps towards your very first exploit payload. We're going to go over a number of other examples and cover polymorphic shellcode. We're going to, however, focus solely on Linux, and we're also going to wrap up and cover position independence and have some demos. Next time, we're going to cover how the process memory map differs for Windows, and we're going to dive into heap exploitation and format string exploitation, as well as exploit mitigations for native code security, otherwise known as executable security mitigations, ranging from stack cookies to ASLR to DEP, NX, and several others, as well as the ways they are weak and what attackers use to bypass them. So a good resource for the slides is the Shellcoder's Handbook, as well as the Art of Exploitation textbook. Shellcoder's Handbook is decently up to date. It's growing old though, and it's important to cover this stuff because exploits and shellcode doesn't rain from the heavens. So like every now and then, oh my God, there's an O day. Let's plug it into Metasploit. It takes a moderate amount of skill to develop exploits. Often, for very harder ones, it takes an immense amount of skill. And so there are a lot of tools in this domain. Often a hex editor is going to be one of your most commonly used tools, as well as some sort of assembler, some sort of disassembler, some sort of compiler, some sort of debugger, a linker, something for also editing raw data like a hex editor, perhaps just for extracting. DD is useful for that. And some form in which you can test your shellcode. The above tests, I believe, just simple shellcode, networking shellcode written in C and x86. And there can be different syntaxes for the instruction set of your choice. For x86, there's commonly AT&T syntax and Intel syntax. And as our guest lecturer said, that most everyone nowadays uses Intel syntax. So if you're using GDB, the way to set it, because it defaults to AT&T syntax, which can be confusing if you're coming straight from the slides and straight from the Art of Exploitation textbook. I should note that the other textbook I suggested, Shellcode, the Art of Exploitation, the Shellcoder's Handbook, I apologize, prefers AT&T syntax. To set your syntax flavor, you basically do set disassembly flavor, Intel or AT&T. For GCC, you tell it Intel. For NASM, the default is Intel. For object dump, the default is AT&T, so you capital M. Intel will tell it to disassemble in Intel syntax for x86 instructions. So shellcode is a set of instructions that's injected and executed by a whole program in an exploit. And originally, the main purpose was to spawn a shell. It now refers to any exploit code at this level and is used to directly manipulate program registers, processor registers rather, and the execution of a program. It's thus generally written in assembly code and then translated to hexadecimal opcodes by assembling it, linking it. And there are often very subtle nuances that you have to pay attention to when working at this level. And these nuances are often processor specific, operating system specific, and then sometimes they can be also library, compiler, and virtual machine, sandbox, etc. specific. Um, and we're going to have to learn how to write our own shellcode so that if you see it, not only in a pen testing standpoint, but also an incident response standpoint, you are able to identify it, reverse engineer it, and figure out exactly what the attackers are doing to your system. That's why we're covering it. So in order to understand how to write shellcode, we're going to have to understand system calls. This is not the same as the previous example that I started with, system function provided by libc, or any other library calls. System calls are provided as an interface to the operating system. You should remember that. They're very different in A, style, B, calling convention, and C, functionality than functions provided by libraries. They often also completely differ per operating system. So system calls are extremely powerful and allow access to operating system level functions. And in order to trigger them, usually the processor has to switch from user mode to kernel mode, and that requires a full context switch, some performance overhead as well. So there are two common methods for executing a system call in Linux. You can call the libc wrapper, so execv, etc. Well, I'm sorry, that's the system call directly. Or you can call the system call directly with assembly. So you load the appropriate arguments on the stack, and then you call interrupt 0x80. So int 0x80 is the most classic way of directly calling system calls in assembly. There are alternative methods that I've heard of in different trap numbers, interrupt numbers rather, and we'll touch on them just a little bit. When the interrupt instruction int 0x80 or hex 80 is called, is executed by a user mode program, the CPU switches into kernel mode and executes the function. The function is specified usually by some sort of index into a table of system calls. So for Linux, this can differ from standard Unix, as Linux implements the fast call convention for calling system calls. And this provides somewhat higher performance, and effectively the specific system call is loaded into EAX register. Instead of being put on the stack as an argument, it's loaded into the register. And then the rest of the arguments are placed into EBX, ECX, EDX, and etc. For if you pass it enough arguments, they will start being put on the stack. And then the instruction int 80 is executed. CPU then will switch to kernel mode, and the syscall function will then begin executing. So each system call has a unique integer value, and let's jump to system call table for, what is this? The Linux 2.2 kernel. So this is a little outdated, but it gives you an example. So if you were set EAX to 1, that would specify the exit system call. If you set EAX to 2, that would specify the fork system call, etc., etc., etc. And this table specifies what EBX will contain, ECX, EDX, ESI, EDI, etc. I don't believe anything goes, nope, some things may go past EBI, as I suggested. So, with that under our belts, often the registers, instead of containing an entire string or an entire structure, will contain a pointer to whatever it needs. And that's the common way of doing things, even on the stack. So the most basic, absolutely basic system call is exit. It takes in one parameter, and it then just calls in tox80 after setting EAX to 1. So let's see how this works in assembly. I have some very basic, oh, that's too soon. For this code, if we compile this, it will disassemble to the following code for the function exit. It will move EBX some value, then it will move EAX to OXFC. Obviously this is a different and then it will run this, and then it will move EAX1. And you can see there are two system calls. It's been a while since I updated these slides. So what's going on here is that it's doing some system call here for the handler for exit, and then finally running exit. So this previous system call, whatever FC is, I could look it up, but it hardly matters, is obviously doing some form of cleanup, and it's indexed in the system call table specified as FC, and then its first parameter is being passed here. So OXFC is 252, and this corresponds to exit group, so it exits the group for the process and then exits the rest. Very, very simple, and it illustrates how this works. So what we're interested in is triggering this with raw instructions and injecting these into a process. And in order to do this, you may have to be aware of the other ways the system calls may be pulled off. As I said, the int80 classic implementation has a very high overhead, and there have been some optimizations added in the forms of alternatives. As at the start of Pentium 2, Intel added in sysenter as a alternative for int80. So if you call sysenter, it will handle similarly. Also, AMD similarly put in syscall, and then Linux at the 2.5 kernel iterations began with the free syscall page. Basically, virtual system calls and the virtual system call page are maintained by the kernel, allowing for faster running of kernel mode stuff without so much overhead of the full context switch, if I recall correctly. It's also important to keep in mind that compilers may do all this stuff differently, so that's another nuance to be aware of. So let's write some shellcode just to pull out the basic exit. So we're going to want to store 0 in EBX, we're going to want to store 1 in EAX, and then we're going to want to call int 0x80. And so the following assembly code will perform this. We set the start function to first run move 0 into EBX, then move 1 into EAX, then to call int 0x80. If you save this as exit shellcode.asm or something.asm, you'll use the NASM assembler to create your object file. There we go. And NASM-FELF will tell it to specifically to create a ELF format executable, and then the loader will load in the rest. And when we go to disassemble it with object dump, you're going to see that these are the corresponding opcodes for each of these instructions. So move EBX 0, move 0 into EBX is BB 00000000. So it's 5 bytes wide. The next one is 5 bytes wide. The next one is 2 bytes wide. It's rather simple. So when you convert this into a character string, you're going to have in C the /x escapes and tells it to specify the following two characters as a raw byte, obviously limited to 0 through 9, A through F, to BB /X BB /X00 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 /X00, and so on and so on and so on. Very, very straightforward, but this is an important concept to understand. So, given the following code, I have it running here in this VM, if we tell it to compile it, and then we run it, we can't really tell what it's doing. We're telling it to exit right away. So what we're going to have to do is trace the system call to see what's going on. And you'll see that the very last thing that's being called is indeed exit. However, this works. This is great. However, there's a problem. If you try to enter this into a buffer for a program, this is not going to work. You have null characters, and any string copy operation is going to terminate on the first null character it finds. It doesn't care what happens after, what occurs in the string after that. You could have the rest of your payload. It's going to truncate it right there. So null bytes are a specific problem for string copy and often array-oriented copy operations. Anything that relies on terminating on a null byte or any other terminator has this style of problem. So this would be completely unusable in a real-world exploit. So there are two common methods to get around this. You can replace the assembly instructions with other instructions that create nulls accordingly, but those have to all run prior to it. And that's going to be self-modifying code. Or you craft the shell code so that there are no nulls at all. So either you add the nulls in at runtime, or you craft it so there are no instructions that have null bytes. So you replace any assembly instructions that have null bytes with instructions that do not. So this involves playing with things like XOR, playing with the subparts of registers like the lower half, upper half, and we're going to cover the art of self-modifying code actually in this lecture as well. It's not too difficult actually. So let's replace these instructions with similar instructions that don't have any null characters. And a very, very useful tool for this is something provided by Metasploit called NASM shell. And you'll usually find it titled nasm_shell.ruby, and you can find it with this command Metasploit running backtrack. And so we'll see that move EAX1 produces the opcodes B8, 01, 00, 00, 00. These trailing 0 bytes are the problem. Anything that precedes it is actually not a problem. And to clarify, this specifies the line number, so this is line 0. So if we do like XOR, EAX, EAX, and then INC EAX, that would be one way to set EAX to 1. Another way would be to move perhaps into the lower byte 1. And this does not produce a null byte. You do see two zeros side by side. However, this would be the first byte and this would be the second byte, and that's the way that things are aligned. Period. So the way we rewrite these is instead of moving 0 into EBX, we XOR EBX, EBX, And then instead of moving 1 into it, we can move 1 into the AL register. And to recap, the AL register is the lower 8 bits of the AEX or RAX register, and this is left over from the very, very old days for backwards compatibility. And a lot of things that are left in for backwards compatibility are often very convenient during exploitation. So this is our new assembly code, and you'll see that when we put it all together, there are no null opcodes, and this is great. The shellcode is also much smaller, and this is actual shellcode that you could inject into a process, this buffer, that would cause it to exit. Not very useful. So let's recap here that there are 5 steps I suggest for writing useful shellcode. You first use a high-level language to write the desired shellcode, and we're going to explore another example with that. And you compile and disassemble a high-level shellcode program. You analyze how it works at the lowest level, the assembly level, and you clean it up, you compact it, you make it injectable, you extract the opcodes to create the shellcode, and you should be good. So let's start from a basis, and we want to be able to execute arbitrary binary. And this would be the code to execute binsh with execve. And execve takes 3 arguments: a pointer to a string that specifies a file name, pointer to an array of arguments, and then a pointer to an array of environment variables, which can often just be completely null. So what we need is position-independent shellcode that we can inject, because when we put something into a process that we're targeting, we usually cannot attach a debugger to it. We usually cannot figure out without a memleak what the stack looks like at a specific address. And so we need some way of having it so that our shellcode is not fragile and doesn't rely on it being located at a very, very specific address in order to work. It needs to be position independent. So this is a difficult task, but there are ways to do it, and usually short jumps allow you to do this, and we're going to explore that just a little bit, but I don't want to get too far ahead of myself. So, like I said, execve, this is the target system call. We're going to use this to spawn a new shell. It takes 3 arguments. They must all be pointers. The first argument is going to be a pointer to a string. The string specifies what it's going to execute. In this case, it's going to be binsh. The next pointer is going to be to an arguments array. And in most cases, the very first argument is just going to be also the name of the file. Then a pointer to the environment array can be left as completely null, will have to be pointed in as well. So EAX is going to be the system call for execve. EBX is going to be a pointer to the string in the binary to execute. ECX is going to be a pointer to the arguments array. And EDX is going to be a pointer to the environment array, or a pointer to something that's null. Not a null pointer, but a pointer to something that is null. So, like I said, hard-coded addressing makes fragile shellcode, and relative addressing makes position-independent shellcode. And so, EAX will hold the integer number for the address of the execve system call, and we've already covered the rest of this. So, what we're going to do is take the C code that we've shown on the previous slide, compile it, and we're going to look at it. And this may be really intimidating to look at, but bear with me. We're going to use this to help us understand what to do. So, looking just at execve, because this is where the action occurs, we see that it's moving into EAX, the value OXB. Then the next things, judging by the arguments to this, is that this is the second argument, and it's moving into EBX. This is the third argument. No, this is the third argument, and it's moving it to ECX, and this is the fourth argument, and it's moving it to EDX, and then it calls int 0x80, and then boom, it's done. So we're going to have to find some way to hold the address, to hold the string binsh and have it be null terminated. And we're also going to have to find some way to hold a null terminated array of arguments. We're only going to need one argument, the program name. And we're also going to have EDX point to a null terminated environment array. So there's a lot of nulls we have to add in. Obviously, we can't just have them statically in there. So let's walk through this assembly code that is not only position independent, but does all of this, almost. So the first thing that it does is say when the processor jumps right here, all right, it's going to set the return address to wherever it was previously in the .text segment. Say we're storing this on the stack. So the return address is pointing there. The stack pointer is pointing somewhere perhaps independent of this. And if we tell it to short jump allows you to jump forward or backwards by X number of bytes. It doesn't require jump to exactly this address, which would be hard-coded addressing. It is instead relative addressing. So short jump is the way to go. So we're going to short jump down to part 2, and when we put this all together, it determines exactly the number of bytes to do this, and we don't have to calculate by hand. And then what we do is we call part 1. By jumping back here, we set it up so that this point is pushed onto the stack as the return address. And so if we use it accordingly, we can manipulate the rest of this string. So let's keep that in mind as we go forward. If we pop the stack at this point, this is going to have the address of our string because it's going to have the return address. And normally here is where you would expect the function prolog where it saves EBP, it moves ESP to the appropriate place, and then it's making room for the local variables, and then it sets the local variables, etc. Instead, what we're doing is we're exploiting the fact that call saves the return address. So by popping the first thing, we're going to pop the address here. So EBX now has the address to a string that contains binsh. However, it has all this extra crap on it. This is just a dummy placeholder to demonstrate what we're doing. So we're going to zero out EAX. And then what we're going to do is, with EAX now it's a null register. It contains all zeros. If we move 1 byte, 8 bits, into EBX plus 7, so that's 1, 2, 3, 4, 5, 6, 7. So EBX would point here, so 1, 2, 3, 4, 5, 6, 7. If we replace X with 0, then we're great. So then this has now been null terminated by this operation. Now what we want to do is move the string EBX, the pointer stored in EBX now, to EBX plus 8. So it's going to overwrite 1337 with the address also to binsh. And then what we do here is we put EAX, which has been 4 null bytes because it's been zored out. We now overwrite all of B055 with a null terminator. So it's completely null terminated. So we now load the effective address for EBX plus 8 into ECX. So ECX is now pointing to where 1337 has been overwritten. Okay? EDX is now being overridden with a pointer to zeros. So it's pointing to a null D word. That's perfect. ECX is pointing to an array, and the first thing is pointing to bin sh. The next thing, it looks at the next D word, is, oh, that's already been zeroed out. So we're using the B055 here twice. We're using it once to terminate the array for ECX, and we're using it again to be just a null terminate array for EDX. Brilliant. Then we set up EAX to have the appropriate system call number, and we call intox80, and that's what we'll launch. Hopefully you all understand that. So when we put this all together and we look at it, there's going to be a problem. If you just look at the binary, there's 0 standing all alone, and we won't be able to inject this into a buffer. So we're going to have to make a little bit of modifications, and this is pretty typical when you're writing shellcode, having to do this step. As a note, if I haven't said so already, if you just run NASM as without any file specifier, it's going to create raw binary, and if you try to look at it, it's not going to know what to do. So you're not going to be able to do anything like object dump disassembly with it. It'll tell you file format not recognized, which is why we're looking at it with text dump. Blah, blah, blah. So when we look at it, the null bytes are specifically caused by move 11 or 0xb into EAX. And we're going to find some way to move 11 into EAX without triggering these null bytes. So, blah, blah, blah. We move it into AL. And what that gives us is success. Also, the shellcode, I believe, is shorter. So, we have the following shellcode, and we now have move AL and move 11 into AL, and we're going to, whoops, this is the right terminal, see that it indeed has no mouse. Stop messing up. I hate this VM. It has no null bytes, and say we have this process dot slash, we have this process form, and it does some form, oops, something, and if we give it a very large string, perhaps it's going to crash. Indeed, it's seg false. So what we're going to demonstrate is the efficacy of this position independent shellcode, and I have it somewhere in yes. Alright, so let's indeed verify that there are no null bytes, and we can see that it looks like there are no null bytes. So just for the sake of demonstration, we're going to again put this in an environment variable and just demonstrate really simple, crappy privesc. Whoops. Alright, so we're going to again do get the environment variable of vuln, of shellcode in vuln. And so if we run vuln now, this is assuming we can view the environment, the stack of vuln, and we tell it to smash the stack with the address to point there, we're going to pull this all off, assuming everything aligns correctly. And we'll discuss that more later. And boom, it worked. So, the shellcode spawned via execve system call in a position-independent manner by using short jumps to rely on the fact that when you do short jumps and calls, that it's going to put a stack address in a reliable place on the stack that you can then use in a relative manner. Privileges. It is very common for applications to drop privileges to a less privileged state or user ID to operate and perform some features. For instance, the code provided here drops privileges. For instance, if this were run as root, UID would be 0, and by setting effective user ID to 5, it's changing to a non-root user and then performing some code, which in just this toy example happens to be a vertical function. But it demonstrates that if this were to be attacked and someone were to pop a shell, it would spawn under the user ID 5. However, nothing prevents an attacker from crafting shellcode that makes the same call and tries to restore privileges. Set RESUID to system calls allow such functionality, and the following shellcode will attempt to restore root privileges. If any one of these is still 0, it may allow the restoration of root privileges. And you can read up on set RESUID. It won't be on the exam, but it's very important to know this technique. And the result, the shellcode after this, simply attempts to spawn a shell, which would hopefully be at root if this were all to work. So before we dive into the rest of the lecture, let's go over some reference slides for shellcode and registers and also process memory space. In 64-bit architecture, instead of EAX, EBX, ECX, everything starts with R, and then there's even more general purpose registers, R8 through R15. And the registers are 64 bits instead of 32 bits, and there's twice the number of general purpose registers. And we're not going to cover Windows shellcode in this class, but it is not like Linux. It is actually exceptionally easy to write Windows shellcode, and the Shellcode's Handbook has a pretty good section on that. I don't think it's in our textbook, The Art of Exploitation, but essentially Windows shellcode involves accessing the provided API for the Windows kernel, which is Win32 API, and the DLLs associated for it. And then you want to load the libraries and get the proc addresses for whatever functions you want to run, and simply just call the procedures. It's relatively that straightforward. The Corelland tutorials, which we suggest later on in this lecture, provide very good introduction to this and are a must if you wish to go into any form of Windows security in this style. So to recap, Linux and Windows process space. Linux, the higher memory here is at the top, and the stack grows towards lower memory. and the heap grows towards higher memory. Um, this is where the dynamic libraries are loaded in. You have the BSS segment, you have the data segment, you have the text segment. And for Windows, um, according to this diagram and from other things that I've found, the stack and the heap are beside each other and they grow apart. And other segments include the .text segment, the data segment, the PE header, and Windows. You also have the process execution block, I believe, and other useful segments. And that covers it for today's lecture. Next time, we'll resume with heap exploitation, and it'll be a very demo-heavy lecture with several examples being exploited. Thanks for watching.